Okay, so now we've seen neural networks in quite a bit of depth. I'm going to introduce the extension, which is deep neural networks. And this is really quite a simple extension because all we do is exactly the same as what we've already seen, but we just do it multiple times. So before, where we just had weights 1 for the first layer, and then we had another weights vector for the output layer, we just add more weights. So we're essentially just learning more stuff. And this basically allows us to learn much more complex features because now these deeper layers are going to become building blocks from some of the earlier layers. The earlier layers are going to become building blocks for the deeper layers. So you can get more powerful features and more expressive features at these layers than you can just from having the one singular layers. So by adding more layers, you sort of allow the network a bit more flexibility with what it's able to do, and you're able to guide it a little bit more in a sense. We'll see what I mean later on. In terms of the maths, often you'll just call this first layer f of 1, and then the next layer will just be like f of 2 of f of 1 of x. So if you remember that this, we call this the hidden layer. So the hidden layer will be f1 of x. So you can think of this now just as h1, and it'll be f2 of h1 instead, if that's easier for you. So it's like for this layer, you're just considering the vector that you get at this stage as your new input. And then you do the same thing for the next layer. And then finally for your output layer, you have this f4. And that's your full neural network now. So your neural network f of x is just a culmination of all of these layers. So exactly the same as what we've already seen. We just have more of the same, basically. So I'm going to talk you quickly through an example. This 7 should be familiar to you by now from the MNIST dataset. And the first stage is that we need to do a little bit of a transformation so that we can put it into one of these neural networks. So instead of having a 28 by 28 image, because we know that we need to have a vector in the first layer, instead of having that image, we do something which is called unfolding, which is very simple. It's just that the first row of this matrix, which is again a vector of numbers. You can think of each row as its own vector. So this vector is going to become the first part of our input vector, and then the second row is going to be the next part of our input vector, which means that we transform this 28 by 28 matrix into a 784 by 1 vector. So this is much bigger than the stuff that we've been looking at so far, where we've just got a 3-dimensional input, a 4-dimensional hidden layer. But the process is exactly the same, it just takes longer to compute. Again, instead of having just 4 neurons in each of these layers, we're going to have 100 neurons, and this is just a design choice. You can pick as many neurons as you want, try lots of different things. The neurons in layer 1 don't have to be the same as the number of neurons in layer 2. This one can be 100, and then this one can be 5, and then we can go back up to 100 if you want. It's completely up to you. Try lots of different things, see what works best. This is a painful, very boring process that we have to do, which is called hyperparameter tuning. But it is essential because all the best results that you're going to get from your network are going to come from tuning these hyperparameters. So the weights that you learn are going to be learned automatically. So the weights, the weight matrices for all of these layers, but the hyperparameters for how big these layers should be, and then how many layers you want, some other stuff like what activation function you use, what dropout rate you use. All that stuff is for you to iterate on, and that's what we're going to be looking at in the iterative development phase, the iterative development mission that will be your team task. So yeah, this is something that you can just play around with, and we're going to get a score for each of these 10 classes. So the first element of this output vector is now going to be the class representing the number 0. The second element is going to be the class representing the number 1, etc. So we are going to get a confidence score as an output. So before I get into that, I'll just talk about this softmax function very briefly. What we don't want is for this, like, we don't want this to be like 0.3 and then this is 0.05 and this one's 0.1, etc. What we want is for these to be very, very polarized, so that we have something like this, where we have one number that's very big and lots of numbers that are very, like, 0 or very, very close to 0. And the softmax is going to do that for you. And I'm going to explain this in more detail in lecture 5. So the reason that we get a confidence score of 15% for 1 is that the number 1 already looks quite a lot like number 7. I'm going to explain this in a bit more depth on the next slide. But if we go back to how we, when we talked about representations, each of these hidden layers is essentially going to be a new representation of this input data. And then when we look at the manifold of the numbers that we'd have in the MNIST dataset, let's say that the number 7 is in red, then all the number 7s are going to be hopefully around here, quite close to one another. But the number 1s are, if the number 1s are in blue, they're going to be very close to the number 7s as well. Whereas stuff like, if we have another colour, I'm going to go with purple. If we have the number 3, let's say, we'd hope that they'd be like way off over here, because a number 3 doesn't look anything like a number 7 or a number 1. So yeah, this is going to be the final output that we get, and we can see that it's doing quite well. The next slide is going to give you a bit more of a bit more detail in how this might look in practice. So what I want to do here is quickly inspect what these features might represent, so what each of these individual neurons would represent, and how they work together. So you can see in the first layer, if I switch back to red, in the first layer we get very, very small sort of building blocks of these features, and as we get to deeper layers, the features represent something which is a lot more complete. And we can actually explicitly see this when we look at convolutional neural networks, but for this it's a lot more fuzzy because these are just a collection of weights, right? But what I want to draw your attention to is this second layer here is going to be, the features here are just going to be a weighted sum of the features we have before. So if you remember, we're going to have, if this is H1 plus H2, H3, etc. If you remember when we talk about this, how these features come about and what this one is going to look like, this neuron is going to be W1 times H1 plus W2 times H2. So you can think of these white squares with the feature inside as these hidden representations. And these are all going to have a very, very high weight because when you can see visually here, when we add all of these bits up, you're going to get this outcome. So if I write in green, these are all going to have a very high weight, and the other neurons are going to have a much lower weight because we don't need them. And it's going to be the exact same thing when it comes to these final outcomes. So if you remember the number 7, the number 7 is going to be an addition of these features, and the ones that look most like that is this one here and this one here. So we'll just go there. So these two, the weights here are going to be very, very high. And the weights for the other features are going to be hopefully very, very low. So you can see that the 7 is going to be, if we say that this is 1, you can't really see that. But yeah, if we say that these green lines just represent 1, and then all the other lines represent 0, you can see how we get a representation for this number 7 based on this mid-level feature and this mid-level feature. These mid-level features are based on the early level features. So that's how you can get more expressive features when you design deeper networks compared to the shallow networks we looked at in previous videos.